Welcome to this course on compilers. My name is Alex Aiken. I'm a professor here at Stanford University, and we're going to be talking about the implementation of programming languages. There are two major approaches to implementing programming languages, compilers and interpreters. Now, this class is mostly about compilers, but I do want to say a few words about interpreters here in the first lecture. So what does an interpreter do? Well, I'm going to draw a picture here. This box is the interpreter, and it takes, and let me label it with a big I, it takes as input your program that you wrote and whatever data that you want to run the program on, and it produces the output directly, meaning that it doesn't do any processing of the program before it executes it on the input. So you just write the program and you invoke the interpreter on the data, and the program immediately begins running. And so we can say that an interpreter is online, meaning the work that it does is all part of running your program. Now a compiler is structured differently. So we can draw a picture here, which we'll label with a big C for the compiler. And the compiler takes as input just your program, and then it produces an executable. And this executable is another program. It might be assembly language, it might be bytecode, it could be in any number of different implementation languages. But now this can be run separately on your data, and that will produce the output. Okay? And so in this structure, the compiler is offline, meaning that we pre-process the program first. The compiler is essentially a pre-processing step that produces the executable, and then we can run that same executable on many, many different inputs, on many different data sets, without having to recompile or do any other processing of the program. I think it's helpful to give a little bit of history about how compilers and interpreters were first developed. So the story begins in the 1950s, and in particular with a machine called the 704 built by IBM. This was their first commercially successful machine, although there had been some earlier machines that they had tried out. But anyway, the interesting thing about the 704, once customers started buying it and using it, is that they found that the software costs exceeded the hardware costs. And not just by a little bit, but by a lot. And this is important because the hardware in those days was extremely expensive. And even then, when hardware cost the most in absolute and relative terms, more than it would ever cost again, already the software was the dominant expense in making good use out of computers. And this led a number of people to think about how they could do a better job of writing software, how they could make programming more productive. One of the earliest efforts to improve the productivity of programming was called speed coding, developed in 1953 by John Backus. Now, speed coding is what we would call today an early example of an interpreter. And like all interpreters, it had some advantages and disadvantages. The primary advantage was that it was much faster to develop the programs, so in that sense the programmer was much more productive. But among its disadvantages, speed code programs were 10 to 20 times slower than handwritten programs, and that's also true of interpreted programs today. So if you have an implementation that uses an interpreter, it'll typically be much slower than either a compiler or writing code by hand. And also, the speed code interpreter took up 300 bytes of memory. And that doesn't seem like very much. In fact, 300 bytes today would seem like an incredibly tiny program. But in those days, you have to keep in mind that this was 30% of the memory on the machine. So this was 30% of the entire memory of the 704. And so the amount of space that the interpreter took up was itself a concern. Now, speed coding did not become popular, but John Backus thought it was promising, and it gave him an idea for another project. The most important applications in those days were scientific computations, and programmers thought in terms of writing down formulas in a form that the machine could execute. John thought that the problem with speed coding was that the formulas were, in fact, interpreted. And he thought if first the formulas were translated into a form that the machine could execute directly, that the code would be faster, and while still allowing the programmer to write the programs at a high level. And thus was the Formula Translation Project, or Fortran project, born. Now, Fortran ran from 1954 to 1957. And interestingly, they thought it would only take them 1 year to build the compiler, but it wound up taking 3. So just like today, they weren't very good at predicting how long software projects would take. But it was a very successful project. By 1958, over 50% of all code was written in Fortran. So 50% of programs were in Fortran. And that is very rapid adoption of a new technology. We would be happy with that kind of success today. And of course, at that time, they were ecstatic. And everybody thought that Fortran both raised the level of abstraction, improved programmer productivity, and allowed everyone to make much better use of these machines. So Fortran 1 was the first successful high-level language, and it had a huge impact on computer science. In particular, it led to an enormous body of theoretical work. And one of the interesting things about programming languages, actually, is the combination of theory and practice, because it's not really possible in programming languages to do a good job without having both a very good grasp of fairly deep theory and also good engineering skills. So there's a lot of very good systems building material in programming languages, and typically it involves a very subtle and fruitful interaction with theory. And this is one of the things that I think that's most attractive about the area as a subject of study in computer science. And the impact of Fortran was not just on computer science research, of course, but also on the development of practical compilers. And in fact, its influence was so profound that today modern compilers still preserve the outlines of Fortran 1. So what was the structure of Fortran 1? Well, it consists of 5 phases: lexical analysis and parsing, which together take care of the syntactic aspects of the language; semantic analysis, which of course takes care of more semantic aspects, things like types and scope rules; optimization, which is a collection of transformations on the program to either make it run faster or use less memory; and finally, code generation, which actually does the translation to another language. And depending on our goals, that translation might be to machine code, it might be to a bytecode for a virtual machine, or it might even be to another high-level programming language. Well, that's it for this lecture, and next time we'll pick up here and talk about these 5 phases in more detail. Welcome back. In this second half of the lecture, we'll continue with our overview of the structure of a compiler. Recall that a compiler has 5 major phases: lexical analysis, parsing, semantic analysis, optimization, and code generation. And now we're going to briefly talk about each one, and we're going to explain how a compiler understands these with an analogy to how humans understand English. The first step in understanding a program, both for a compiler and for a human, is to understand the words. Now, humans can look at this example sentence and immediately recognize that there are 4 words: this, is, and sentence. And this is so automatic that you don't even think about it, but there is real computation going on here. You have to recognize the separators, namely the blanks, and the punctuation, things like the periods, and also clues like capital letters. And these help you to divide up this group of letters into a bunch of words that you can understand. And just to emphasize that this is not completely trivial, let's take a look at this sentence. And you can read this, but it takes a little bit of time because I've put the separators in odd places. So you can see the word is, the word this, the word and the word sentence. But again, this isn't something that comes to you immediately. You actually have to do some work to see where the divisions lie because they're not given to you in the way that you're used to. The goal of lexical analysis, then, is to divide the program text into its words, or what we call in compiler speak, the tokens. So here's an example piece of program text now instead of a piece of English text. And let's walk through this and identify the tokens. So there are some obvious ones. There are keywords like if, and then, and else that we want to identify. And then there are variable names, things like x and y and z. There's also constants, things like the number 1 and the number 2. And then there are some operators. Double equals is one, and the assignment operator is another. And here's already an interesting question. How do we know that double equals is not two individual equal signs? How do we know that we want this to be a double equals and not two single equals? Well, we don't know right now, but we'll talk about that in the lecture on how we implement lexical analysis. But we're not done with all the tokens in this example either. There's a few more. The semicolons, the punctuation, are also tokens. And then the separators are also tokens. So here's a blank, that's a token. Here's another blank, that's another token. And then there are lots of blanks here that serve to separate things like the keywords and the variable names and other symbols from each other. And those are the tokens of this example. So for humans, once the words are understood, the next step is to understand the structure of the sentence. And this is called parsing. And as we all learned in elementary school, this means diagramming sentences, and these diagrams are trees. And it's a very simple procedure. Let's look at this example. This line is a longer sentence. The first step in parsing is to identify the role of each word in the sentence. So we have things like nouns and verbs and adjectives. But then the actual work of parsing is to group these words together into higher level constructs. So for example, this particular sentence consists of a subject, a verb, and an object. Okay? And that actually forms an entire sentence. So here we have the root of the tree called a sentence, and that's broken down into constituent parts. The high-level structure, as we said, is subject, verb, object, and then the subject is more complicated, as is the object. And this is an example of parsing an English sentence. The analogy between parsing English text and parsing program text is very strong. In fact, they're exactly the same thing. So here's our little example piece of code again, and let's work through parsing it. So clearly this is an if-then-else statement, and so the root of our diagram of our parse tree is going to be an if-then-else. This if-then-else consists of three parts. There's a predicate, a then statement, and an else statement. And now let's look at the predicate, which consists of three pieces. There's a variable, a comparison operator, and another variable. And together those form a relation. So a comparison between two things is one of the things you can have as a valid predicate. Similarly, the then statement consists of an assignment where z gets 1, and the else statement also has the form of an assignment, z gets 2. And altogether, this is a parse tree of the if then else, showing its structure, breaking it up into its constituent pieces. Now, once we've understood the sentence structure, the next step is to try to understand the meaning of what has been written. And this is hard. So actually, we don't know how this works for humans still. We don't understand what happens after lexical analysis and parsing. We do know that people do lexical analysis and parsing in much the same way that compilers lexically analyze and parse programs. But frankly, understanding meaning is something that is simply too hard for compilers. So the first important thing to understand about semantic analysis is that compilers can only do very limited kinds of semantic analysis. And in particular, the kinds of things that compilers generally do are try to catch inconsistencies. So if the program is somehow self-inconsistent, compilers can often notice that and report errors, but they don't really know what the program is supposed to do. As an example of the kind of thing that we do in semantic analysis, again, using an analogy in English, let's consider the following sentence. Jack said Jerry left his assignment at home. And the question is, who does his refer to here? It could be that his refers to Jerry, in which case we would read, Jack said Jerry left Jerry's assignment at home. Or it could refer to Jack, in which case we could read the sentence as, Jack said Jerry left Jack's assignment at home. And without more information, we actually don't know which one his is referring to, whether it's Jack or it's Jerry. And even worse, let's take a look at this sentence down here. Jack said Jack left his assignment at home. And the question is, how many people are actually involved in this sentence? It could be as many as 3. There could be 2 separate Jacks, and his could even refer to somebody completely different. We don't know, without seeing the rest of the story that surrounds this sentence, all the possibilities for his. But it could also be as few as only a single person. It could be that Jack and his are all the same person in this sentence. And so this kind of ambiguity is a real problem in semantic analysis. And the analogy in programming languages is variable bindings. So we would have variables, in this case, a variable called Jack, and maybe more than one variable called Jack. And a programming language is going to have very strict rules to prevent the kind of ambiguities we had in the English sentences on the previous slide. So, in this example, the question is, what value is printed by this output statement? And the answer is it's going to print 4, because this use of the variable Jack binds to this definition here, and the outer definition is hidden. So the outer definition is not active in this scope because it's hidden by the inner definition. And that's just a standard rule of a lot of lexically scoped programming languages. Now, compilers perform many semantic checks besides analyzing the variable bindings. And so here's another example in English. So Jack left her homework at home. And under the usual naming conventions, assuming that Jack is male, we know there's a tight mismatch between Jack and her. So we know that whoever her is, it is not Jack. And therefore, we know that this sentence is talking about 2 different people. And so this is analogous to type checking. The fourth compiler phase, optimization, doesn't have a very strong counterpart in everyday English usage, but it's a little bit like editing. And in fact, it's a lot like what professional editors do when they have to reduce the length of an article to get it down to some word budget. So for example, I have this phrase right here, but a little bit like editing. And if I didn't like it, if I thought it was too long, I could replace the middle 4 words with 2 words, akin to. So now it says, but akin to editing. And that means exactly the same thing as the original phrase, but uses fewer words. And the goal in program optimization is to modify the program so that it uses less of some resource. Maybe we want to use less time. We want the program to run faster. Maybe we want it to use less space so that we can fit more data in memory. For a handheld device, we might be interested in reducing the amount of power that it uses. If we have external communication, we might be interested in reducing the number of network messages or the number of database accesses. And there's any number of resources that we might want to improve the program's use of. So here's a simple example of the kinds of optimizations a program might do. We can have a rule in our compiler that says x equals y times 0 is the same as x equals 0. And this seems like a real improvement because instead of doing the multiply, we can just do an assignment. So we save some computation by doing that. Now, unfortunately, this is not a correct rule. And this is one of the important things to know about compiler optimization is that it's not always obvious when it's legal to do certain optimizations or not. Now, it turns out that this particular rule is valid for integers. Okay, so if x and y are integers, then multiplying by 0 is always the same thing as just assigning 0. But it's invalid for floating point. And why is that? Well, because you have to know some details of the IEEE floating point standard, but there is a special number in the IEEE standard called not a number. And it turns out that not a number, called a nan, times 0 is equal to not a number. And in particular, not a number times 0 is not equal to 0. So if x and y are floating point numbers, you can't do this optimization. And in fact, if you did this optimization, it would break certain very important algorithms that rely on the proper propagation of not a numbers. Finally, the last compiler phase is code generation, often referred to as code gen. And code gen can produce assembly code. That's the most common thing that a compiler would produce. But in general, it's a translation into some other language. And this is entirely analogous to human translation. So just as a human translator might translate English into French, a compiler will translate a high-level program into assembly code. To wrap up, almost every compiler has the 5 phases that we outlined. However, the proportions have changed a lot over the years. And if we were to go back to Fortran 1 and look inside of that compiler, we would probably see a size and complexity that looks something like this. We'd have a fairly complex lexical analysis phase, an equally complicated parsing phase, a very small semantic analysis phase, a fairly involved optimization phase, and another fairly involved code generation phase. And so we'd see a compiler where the complexity was spread fairly evenly throughout, except for semantic analysis, which was very weak in the early days. And today, if we look at a modern compiler, you'll see almost nothing in lexing, very little in parsing, because we have extremely good tools to help us write those 2 phases. We would see a fairly involved semantic analysis phase. We would see a very large optimization phase. And this is, in fact, the dominant component of all modern compilers. And then a very small code generation phase, because, again, we understand that phase very, very well. That's it for this lecture. Future lectures will look at each of these phases in detail. Hello. In this video, we're going to talk about something that I've referred to as the economy of programming languages. So the idea behind this video is that before we get into the details of how languages are implemented or designed, I want to say something about how languages work in the real world and why certain languages are used and others are not. And if you look around, there's actually a few obvious questions that come up to anybody who thinks about programming languages for more than a few minutes. One question is, why are there so many of these things? We have hundreds, if not thousands, of programming languages in everyday use, and why do all of these things need to exist? Why wouldn't one programming language, for example, be enough? A related question, but slightly different, is why are there new programming languages? Given that we have so many programming languages already, what is the need for new ones to be created? And finally, how do we know a good programming language when we see it? What makes a good programming language and what makes a bad programming language? And I just want to spend this video anyway talking about these 3 questions. And as we'll see, I think the answers to these questions are largely independent of the technical aspects of language design and implementation, but very interesting in their own right. So let's begin with the question of why there are so many programming languages. And at least a partial answer to this question is not too hard to come by. If you think for a few minutes, you'd realize that the application domains for programming have very distinctive and conflicting needs. That is, it's very hard to design one language that would actually do everything in every situation for all programmers. And let's just go through some examples. One domain that you might not think about very much is scientific computing. So these are all the big calculations that are done for engineering applications primarily, but also big science and long-running experiments, simulation experiments. And what are the needs for such computations? Well, typically you need very good floating point support. I'll abbreviate that as FP. You need good support for arrays and operations on arrays. okay, because the most common data type in most scientific applications is large arrays of floating point numbers. And you also need parallelism. Okay. Today, to get sufficient performance, you really have to exploit parallelism in these applications. And not every language actually supports all of these things well. And this is actually not an exhaustive list of the things you need, but it's a few distinctive things that are needed. But one language that has traditionally done a very good job of supporting these things is Fortran. And Fortran is still heavily used in the scientific community. It was originally designed for scientific applications, if you recall. The name means formula translation. And it has evolved over time. It doesn't really look much like the original language anymore, but it's always retained this core constituency in scientific computing and remains one of the leading languages in that domain. Now, a completely different kind of domain is business applications. And so what do you need here? Well, so here you're going to need things like persistence. You don't want to lose your data. You know, businesses go to a lot of trouble to get the data, and they need a way to hold on to it. They don't want, and they want that to be extremely reliable. You're going to need good report facilities, okay, because typically you want to do something with the data, so you need good facilities for report generation. And also, you want to be able to exploit the data. The data is actually, in many modern businesses, one of the most valuable assets. And so you need good facilities for asking questions about your data. Let's call it data analysis. And again, this is not an exhaustive list of things that you need, but it is representative, I would say, and probably the most common, or one of the most commonly used languages for this class of applications is SQL, the database query language. So relational databases and their associated programming languages, I should say, but most notably SQL, really dominate in this application domain. And then another domain, let's do one more, is systems programming. So by this I mean things like embedded systems, things that control devices, operating systems, things like that. And what are the characteristics here? Well, we need very low-level control of the resources. The whole point of systems programming is to do a good job of managing resources, and so we really want fine-grained control over the resources. And often there's a time aspect, so you might have some real-time constraints, so you need to be able to reason about time. Right? Because these are actually, again, devices, and they need to be able to react within certain amounts of time. You know, if it's a network device or something like that, you need to be responsive to the network. Lots and lots of things, lots and lots of examples where timing is important. And these are just two aspects, and I'm running out of space here, so I'll just stop with that. But again, these are representative of the kinds of things you need in systems programming. And probably today, still the most widely used systems programming language or family of systems programming languages is the C and to some extent C++ family of languages. And as you can see, these, the requirements in these different domains are just completely different from each other. What's important in one domain, or most important in one domain, is not the same as in another domain. And it's easy, I think, to imagine at least that it would be difficult to integrate all of these into one system that would do a good job on all of these things. That brings us to our second question: why are there new programming languages? Okay, well, there are so many languages in existence. Why would we ever need to design a new one? And I'm going to begin the answer to this question with an observation that at first glance has nothing to do with the question at all. So let me just take a moment to explain it. I claim that programmer training is the dominant cost for a programming language, and I think this is really important, so I'm just going to emphasize the bit that's important here. It's the programmer training, the cost of educating the programmers in the language. So if you think about a programming language, there are several things that have to happen for that language to get used. Somebody has to design it, but that's really not very expensive. That's just one or a very few people typically. Somebody has to build a compiler, but that is also not actually all that expensive. Maybe 10 to 20 people for a really large compiler project can build quite a good compiler. The real cost is in all the users and educating them. So if you have thousands or hundreds of thousands or millions of users of a language, the time and money that it takes to teach them all the language is really the dominant cost. And here I don't mean just the actual dollar expense of buying textbooks and taking classes and things like that. It's also the fact that the programmers have to decide that it's worth it for them to learn this language. And many programmers learn on their own time, but that's a use of their time, and the expense of their time is a real economic cost. And so if you think about the number of hours that it takes to teach a population of 1 million programmers a language, that's really quite a significant economic investment. All right. Now, from this observation, we can make a couple of predictions pretty easily. And again, these are just predictions now that follow from this claim, if you believe that it's true. So let me erase that and fix it. So first prediction is that widely used languages will be slow to change. And why should that be true? Well, if I make a change to a language that lots of people use, I have to educate everybody in that community about the change. And so even relatively minor language extensions, small changes to syntax, small new features, even just simple changes in the interface of the compiler, if you have a lot of users, it takes a very long time and is quite expensive to teach them all about that. So as languages become widely used, the rate of change, their rate of change will slow down. And this predicts that over time, as the world of programming grows, as we have more and more programmers in the world, we would expect the most popular languages, which will have larger and larger user bases, so larger and larger programmer bases, to become more and more ossified, to evolve more and more slowly. And I think actually what you see in practice is very consistent with that prediction. Now, at the other end of the spectrum, this same observation makes an almost what appears to be a contradictory prediction, which is that it's easy to start a new language. That in fact the cost of starting up a new language is very low. And why is that? Well, because you start with 0 users. And so there's essentially 0 training cost at the beginning. And then even when you have just a few users, the cost of teaching them the changes in the language is not very high. And it's so new languages can evolve much more quickly. They can adapt much more quickly to changing situations. And it's just not very costly to experiment with a new language at all. And there's a tension between these two things. Okay. When is a programmer going to choose, between a widely used existing language that perhaps doesn't change very quickly and a brand new language? Well, they're going to choose it if their productivity exceeds the training cost. So if they perceive that by spending a little bit of time and money to learn this new language, they're going to be much more productive over a relatively short period of time, then they're going to make the switch. Okay, and so when is this likely to happen? Well, putting this all together, languages are most likely to be adopted to fill a void. Okay, and again, this is a prediction that follows from the fact that programmer training is the main cost. What do I mean by this? Well, what I mean is that programming languages exist for a purpose. I mean, people use them to get work done. And because we're still in the middle of the information revolution, there are new application domains coming along all the time. So there are new kinds of programming that emerge, every few years, or even more often than that. So just in terms of recent history, mobile applications are now something that's relatively new, and there's a lot of new technology being built up to support mobile computing. A few years ago, it was the internet itself was a new programming platform, and a bunch of new programming languages like Java in particular got started during that time. So new programming niches open up because the technology changes, what people want to do with software changes, and this creates new opportunities for languages. The old languages are slow to change, and so they have some difficulty adapting, to fit these new domains, and they aren't really necessarily well suited to them for the reasons we talked about on the previous slide with the previous question, because it's hard to have one language that incorporates all the features you would want. And so there are, so the new languages are not necessarily perfect for these application domains. They're slow to adapt to the new situation, and this tends to call forth new languages. So when there's a new opportunity in some application domain, if there are enough programmers to support the language, often a new language will arise. I just want to point out another prediction that can be made from this one observation, that programmer training, and again I'll underline that, is the dominant cost for a programming language. And that is that new languages tend to look like old languages. That is that new languages are rarely, if ever, completely new. They have a family resemblance to some predecessor language, sometimes a number of predecessor languages. And why is that? Well, partly that it's hard to think of truly new things, but also I think that there's an economic benefit to this. Namely, that it reduces the training cost. By having your new language look like an old language, by leveraging off what people already know about the old language, you make it easier for people to learn the new language. You make them learn it more quickly. And the most classic example of this is Java versus C++, where Java was designed to look a lot like C++. And that was, I think, very conscious to make it easy for all of the existing C++ programmers to start programming in Java. Finally, we can ask ourselves, what is a good programming language? And here, unfortunately, the situation is much less clear. I would just make one claim, that there is no, and I'll emphasize no, universally accepted metric for language design. And what do I mean by that? Well, I guess the most important part of this statement is the universally accepted bit. So I mean that people don't agree on what makes a good language. There are lots of metrics out there, and people have proposed lots of ways of measuring programming languages, but most people don't believe that these are very good measures, and there is certainly no consensus. If you just look at the world of programmers, they can't agree on what the best language is, and to convince yourselves of this, just go and take a look at any of the many newsgroup posts where people get into semi-religious arguments about why one group of languages or a particular language is better than another language. But even in the research community, in the scientific community, and among the people who design languages, I would say that there is no universally accepted consensus on what makes a good language. And to just kind of illustrate the difficulties in trying to come up with such a metric, let me discuss one that I've heard people propose in all seriousness, and that is that a good language is one people use. And let me put a question mark on that, because I don't believe this statement, and I think a moment's reflection, with a moment's reflection, I can convince you that this isn't a great measure. On the positive side, I guess, the argument for this is that it's a very clear measure. It measures the popularity of the language, so how many people are actually using it, and presumably languages that are more widely used for a good reason. In some sense, perhaps they are better languages. But this would imply, if you believe this and follow it to its logical conclusion, that Visual Basic is the best language, above all other programming languages. And I have nothing against Visual Basic. It's a well-designed system, but I don't even think the designers of Visual Basic would claim that it is in fact the world's best programming language. And as we saw in the discussion that we just had, there are many, many other factors besides technical excellence that go into whether a programming language is widely used or not. And in fact, technical excellence is probably not even the most important reason that a language might be used. It has much more to do with whether it addresses a niche or an application domain for which there isn't a better tool. And then once it's established and has lots of users, of course, there's inertia and history that aided in surviving. And that's why we still have Fortran and COBOL and lots of other languages from long, long ago that we could, if we were starting over today, design much better. So to conclude this video on the economy of programming languages, I think the two most important things to remember are that application domains have conflicting needs, and therefore it's difficult to design one system that incorporates everything that you would like to have. So you can't get all the features that you would like into a single system in a coherent design. At least it's very hard to do that, and so it takes a lot of time to add new features to existing systems. And the second point is that programmer training is the dominant cost for a programming language. And together, these two things, these two observations, these really explain why we get new programming languages. Because the old languages are difficult to change, and when we have new opportunities, it's often easier and more direct to just design a new language for those rather than trying to move the entire community of programmers and existing systems to accommodate those new applications.